This video, we're solving exponential equations. These take the form of a constant raised to a variable. So again, in this case, the base is a constant and the exponent is a variable. So we begin by taking the common log of both sides. So log of 3 to the negative 11x plus 6 equals log 5. Next, the purpose of a logarithm is to solve for an unknown exponent. So there's a property of logarithms where exponentiation becomes multiplication. So now my exponent is multiplied out in front. This allows me to solve for it. Now, we could distribute the log 3 into the parentheses, but that wouldn't help us isolate x. We want to get all quantities away from x. Log 3 is just a constant. So we could divide both sides by log 3. So we get log of 5 divided by log of 3. And then this is equal to negative 11x plus 6, but I could subtract 6 to both sides. Finally, divide both sides by negative 11. This is the same as multiplying by the reciprocal. So we get negative 1 over 11 times log of 5 divided by log 3 minus 6. This is our final answer. It's called the exact solution or exact value because it is not expressed as a rounded decimal. And this concept is important in trigonometry, where you may have to express a quantity in terms of fractions and radicals before typing it into the calculator and making it a decimal. Now, if you do type this into the calculator and make it into a decimal, you'll get x is approximately 0.4123. This is the approximate value. Now, there's different methods, especially from textbook to textbook. So I'd like to do the same problem, but using a different method. So I'm still going to repeat 3 to the negative 11x plus 6 equals to 5. In this case, some textbooks or some students like to say, well, instead of taking log of both sides, why not natural log of the left equals natural log of the right? This is perfectly fine too. And we'd get the same result. Exponent becomes multiplication times the natural log of 3 equals ln of 5. Again, although it's tempting to distribute the natural log of 3, we want to move all constants away from x. So I get negative 11x plus 6 equals ln of 5 over ln of 3. And remember, we subtracted both sides by 6 and multiplied by the reciprocal. So we had ln of 5 over ln of 3 minus 6. It's the same exact calculation. Now, the purpose of this exercise is to demonstrate that the ratio of two different logs is equal. So for example, before in our calculation, it looked identical, except we had the ratio of log of 5 divided by log of 3. And this is approximately 1.465. So if you take the ratio of the natural log of 5 to the natural log of 3, it is also approximately equal to 1.465. Therefore, although this calculation involves the natural logarithm instead of the common logarithm, it's still identical. So it uses less symbols, I guess. We write ln instead of log. The other purpose of using natural log is that if our exponential equation contains e, then the natural log would actually cancel with e. So that's really the only advantage behind using ln. So again, why can we take the ratio of any two logs? Even if they have different bases, but the same arguments. Well, that's just a consequence of the change of base formula. So I just figured this is a topic that's really important, just an important concept. Again, even if the logarithms have a different base, but the same quantities in parentheses, the ratio of these logarithms should be equal. Just for repetition, I want to do the same exercise. I know it's a little repetitive, but again, it's just really important to show it could be solved different ways. Because again, what is a logarithm? Well, it's a way for solving for an unknown exponent. So I really like to do this process because it demonstrates that better. Because if I truly want to cancel and solve for my exponent, another approach would be log base 3 of 3 to the negative 11x plus 6 equals log base 3 of 5. I feel like this method better demonstrates the purpose of a logarithm. If the base of my logarithm matches the base of my exponent, they cancel. They're inverses. So this reduces to negative 11x plus 6, just the exponent, equals log base 3 of 5. And then subtract both sides by 6. So we get log base 3 of 5 minus 6. Notice how the parentheses are required here, because I don't want it to look like log of 5 minus 6 as a whole. This becomes x equals negative 1 over 11 log base 3 of 5 minus 6. Again, we recognize that form. It looks very similar to the solution we achieved using the other method, such as a common logarithm. Again, this is a consequence of the change of base formula. Because now I can express this as using the change of base formula. I can express this as a logarithm, such as the common log, which is on my calculator. So log base 3 of 5 can be expressed as log of 5 over log of 3. So we arrived to the same solution as before, as when we used the common log. And again, since we just used the change of base formula, we could have expressed it as the ratio of logarithms with any base. So we could have done base e. So if we did a logarithm with a base e, well, that's the natural logarithm. So we could have also expressed it as the ratio ln of 5 over ln of 3. Again, the ratio of these logarithms should be equal. Okay, so maybe that was a little bland, a little repetitive, but I really wanted to show those 3 different methods in one, because I feel like some students love to use this last method, for example. I feel like it illustrates the purpose of a logarithm the most. It tells me, a logarithm tells me what's the value of the unknown exponent that a base must be raised to give me some number.